77.
Let's take a closer look at atoms. Atoms are the building blocks that make up everything, all stuff, everywhere. Here,
77, page 77. We all on page 77? Excellent.
I've got some drawings. This is table salt, a solid. Here's water, a liquid. And finally, oxygen gas. And what we're looking at here is what we'd see if we could take these three things and zoom in zillions and zillions and zillions of times. And if we could look at these closely enough, we'd be able to see the atoms, these little building blocks that make everything up. Now, atoms aren't really little colored circles, but it's a good way to think about them, and it's the way we'll usually draw them when we're learning about this stuff. Atoms are super tiny. They are so tiny, it can be really hard to wrap your head around how tiny they are. Here is something that might help you think about this. Take a piece of paper. Look at how wide it is here. All right? This is so incredibly thin. Now, atoms are so small that it would take 1 million atoms lined up next to each other in a row to be as thick as this tiny width of paper.
Okay, I want you to picture that right now. I want you to look at an edge of a piece of paper. Okay, just look at it. And think to yourself, how many atoms to get from the top to the bottom? 1 million. Like, how small is that it takes 1 million of them to be that thick? That's crazy small. Okay? How do we know they exist? Because we did experiments, like we did the cathode ray tube experiment, like we did the gold foil experiment. Because they got results and they could see the results and they can do the math and all the good stuff. Yeah. Now, getting back to the idea of just before they were like, what's in the atom, they did actually do some experiments to figure out there were atoms, and what they did is that they found that there were if they took 2 volumes of hydrogen gas, and this was 1 liter, and they put it together with 1 liter of oxygen gas, because they could isolate hydrogen gas and they could isolate oxygen gas, okay? So they knew they had these things. They discovered that they would get exactly 2 liters, 2 volumes of water. Now, how does that tell us that we have tiny little particles? Well, they did some other experiments, and they figured out that every single gas, if you have the same number of particles, it always takes up the same amount of space, okay? So if we have 1 liter, maybe that contains like 1 million, okay? It's probably more than that, but let's say it's 1 million hydrogen particles. So if you take 1 million hydrogen particles plus another million, and you took 1 million oxygens, you will get 2 million water molecules, which tells you that atoms are combining in small whole number ratios. So it tells you that these elements are combining in small ratios, which leads you then to the idea that there is simple little particles that combine in whole number ratios. So if you're like, oh, I have an H2 and I have an O2, I would need 2 of those little H2s to get together with an O2 to make 2 H2Os. There's a little bit more to it than that, but that's the general idea. That's how they got the idea that there were actually like little particles that combined in whole number ratios. Okay? All right. Back to our video.
That's how small atoms are. Now, what I want to do now is look even closer at an atom. Let's take one of these atoms here and zoom in even more so we can see what's inside of it. Here's a magnified view of one atom. It's not a perfect representation of exactly what an atom would look like, but it's close enough for right now.
Okay, and you guys are going to tell me, what is this little blob that contains the blue and red things? That's the nucleus. What are the blue and red particles? Protons and neutrons. And what are those little black things around the outside? Electrons. Which particle gives the nucleus its charge? What charge is the nucleus? Protons, and the nucleus is positive. What charge is the area outside the nucleus? Negative. Okay, very good. And what charge are neutrons? Neutral. So they don't affect the charge at all. What charge is the whole atom? You've got positives in the middle, you've got negatives on the outside, and you'll have the same number of positives and negatives. And if you have the same positives and negatives, what's the overall? 0, neutral. Yeah.
And check this out. The atom itself is made up of even smaller things, right? So that we said atoms are like the building block for all of stuff. But then if you look at an atom, it has even smaller building blocks that make it up. So in the center of the atom is something called the nucleus. And the nucleus is made up of 2 tiny particles. There are protons, which I've drawn as red circles here, and then there are neutrons, which I've drawn as blue circles. Nucleus is here in the middle of the atom. And then on the outside of the atom, there are these little black circles that I'm using to represent electrons. The electrons, you'll see, are connected to these sort of oval paths, and I've drawn these in to show that the electrons are constantly moving. They're flying around the outside of the atom at an incredibly high speed, whereas the nucleus stays solid here right in the middle of the atom. Now, electric charge is very important when we're talking about atoms for a number of reasons. Protons have a positive charge. A proton has a charge of 1 plus. Electrons, on the other hand, have a negative charge. One electron has a charge of 1 minus. Now, neutrons, they don't have an electric charge at all. They have a charge of 0. And neutral is a word that we use to refer to something that doesn't have a charge. So neutrons sounds a lot like neutral. Now, positive and negative charges attract. Remember that? Opposite charges attract. And that has important consequences for how this atom works. We said that these electrons are flying around the outside of the atom. They're moving really fast. So why don't they just fly out into space? Well, the reason why is because the negatively charged electrons are attracted to the positively charged protons. So the protons kind of pull the electrons in. They keep them from just flying away. But the electrons are moving around so fast that they're not able to actually pull in here and actually touch the protons. So that's why they keep staying on the outside and don't just crash in here and all touch the protons. Now, sometimes people ask, well, neutrons don't have a charge. Why are they important at all? Well, it seems that neutrons help keep all of the particles in the nucleus strongly connected to each other.
Let's think about protons. Protons are positive, and they're really, really close to one another, yeah? All our little red protons are close to one another. Do positives like to be close to positives? No, they do not like it at all. So if basically what they think is that the neutrons act like almost like a glue to bind those protons together to keep them from pushing each other apart and to keep the whole atom from exploding. Okay? So that's why they need the neutrons there, is to keep the protons from repelling each other into a big explosion.
Now, electrical charge is important. Something else that's important with atoms is what their mass is, how much they weigh. So in order to figure that out, we have to look at the mass of the various things that make up the atom.
Do you guys remember the particles in the atom that actually have a substantial mass? The protons and neutrons, the stuff in the nucleus, actually has substantial mass. And they each, we can just say they have a mass of 1 each. Okay, we'll talk about what's the unit in a little bit. How about electrons? How do they compare? Like virtually nothing, yeah.
Now, a proton and a neutron are very, very similar in size and in mass. And they both weigh about this many grams.
That's a really small amount of grams, yeah? So it's really, really irritating to have to write that out. So they came up with a new unit that's much, much smaller than a gram to be able to measure these things, because nobody wants to write out that many zeros. That's crazy. You could use scientific notation, but too many zeros.
Look at what a tiny number this is, right? There's a decimal place all the way over here. This is a number that it's best to represent in scientific notation instead.
So if you're interested in what scientific notation is, you see this says 10 to the power of negative 24. Okay, what that means is we have moved our decimal place 3, 6, 9, 12, 15, 18, 21, 22, 23, 24. We moved our decimal place 24 places. Okay, so that's a lot of decimal places to be moved.
But however you write this, it's a really tiny, unwieldy number. So scientists came up with another way to measure the mass of a proton or neutron.
By the way, if you're wondering what the word unwieldy means, unwieldy, it means awkward and just not very easy to use. Unwieldy. Unwieldy.
So scientists came up with another way to measure the mass of a proton or neutron, and that's using a unit called the AMU, the atomic mass unit. And they said, okay, 1 proton or 1 neutron weighs about 1 AMU. That's a lot easier to use than this measurement here. So proton or neutron weighs about 1 AMU. An electron, on the other hand, is much, much, much smaller than a proton or a neutron. It weighs only 0.000549 AMU. So a tiny fraction of how much a proton or a neutron weighs. For this reason, when we're talking about the mass of atoms, which we'll talk about later on, we usually add up the protons and neutrons to find out how many AMUs the atom weighs. And then we usually don't even worry about the electrons at all, because they're so tiny. They don't really have much of an influence on how much an atom weighs. It's like when you get on a scale to weigh yourself, you don't worry about the ring you're wearing or whether you're wearing a necklace or something, because those things are just so tiny, they weigh so little compared to how much you weigh that it doesn't really influence your weight.
So it's like if you were weighing an elephant and a fly landed on the elephant. Would you care? No. It wouldn't make any difference. So we just ignore the electrons. So if you were to say, how much does this atom here, how much does this atom here weigh? What would you have to look at? 9. Well, let's see. We got 1, 2, 3, 4, 5, 6, 7. 7 protons plus neutrons together. Okay? So we would have 1, 2, 3, 4 neutrons and 1, 2, 3 protons. So 4 plus 3 gives us 7. So this has a mass of 7. What's the unit? AMU. What does AMU stand for? atomic mass units. Excellent.
So, protons and neutrons, 1 AMU, and electrons, a tiny fraction of that. Now I said that the atom, the way it's drawn here, isn't a perfect representation of what atoms would actually look like. We'll talk more about that later, but there are two things that I want to bring up for right now. The first is the electrons and how they move. This drawing might make you think that the electrons are spinning around in nice circles on the outside of the atom. That's actually not what happens. They're buzzing around much more randomly, kind of like hyperactive flies all over the place. We'll talk more about that later. The second thing has to do with the size of the nucleus and how far the electrons are from it. If this were a real atom blown up many, many times, and the nucleus were the size of a grape, the electrons out here would be almost a mile away.
Okay, so picture that. The nucleus is the size of a grape. The electrons, they could be anywhere from close to the nucleus to as far as a mile away. And that's just not 1 mile like all together. That's 1 mile in this direction and 1 mile in that direction. So the idea is that the nucleus is extremely tiny and the electrons take up almost all the space. Okay, it's crazy. Crazy, crazy, crazy. And I think that is it for that. So let's go through and make sure we got all of the little things filled in. So this is page 77. Okay. Atoms are the whats for all matter. They are the building blocks. Atoms are super tiny. How many atoms would it take to make a piece of paper? The thickness? 1 million. It is really big. Atoms are the building blocks for all of stuff. But the atom has even smaller building blocks. That make it up. And there are 3 building blocks. What are the little black ones? Electrons. Whoa, that moved around. And what charge are the electrons? Electrons are negative. And then we have this thing in the middle. And this is the nucleus. And then we have protons. And we have neutrons. And the protons are positive. Isn't it nice that P for proton, P for positive? And the neutrons are 0, neutral. Okay, so we can fill those again. The electrons are negative, protons are positive, neutrons are neutral. So the mass of one proton or neutron it is way too many numbers, isn't it? And that's why we say, no, we are not going to write that many numbers. We're just going to say that that is equal to 1 AMU. The mass of one proton, electron. Oh, sorry. And the AMU stands for atomic mass unit. Mass of one electron is like 0.0005 something or other. Just very small. 0.5 what? That's okay. And I just put 0.0005. 549, excellent. An electron weighs a tiny fraction. We usually don't worry about electrons at all. They are so tiny, they do not affect the mass of the atom much at all. So it's just like a ring or a necklace that you're wearing. Those things are so small or tiny, you can just ignore their mass. And so just like that, we ignore the mass of the electrons. The electrons don't actually go around the nucleus in nice circles. They buzz around like hyperactive flies. Yes, very good. If the nucleus were the size of a grape, the electrons would make a cloud that reached out to about a mile away. Yeah, it should be like 1.6 kilometers away. Yeah. 1.6 kilometers. Most of the atom is actually empty space with the electrons buzzing around in that space. Okay, and we're not going to do the worksheet just yet because otherwise we're going to have that thing that happens where half of the people are done all the work and then the other half of the people are still working on the work. So we're going to go ahead and do a little something else and then I'm going to give you the work, okay? So we are now going to go to page 83. We're on YouTube again, yeah. And it's more Tyler. Tyler, our friend, is back. Page 83.
What are isotopes? Isotope is a word that gets thrown around in chemistry a lot. So, like, what are they?
Okay, let's make sure our volume is all the way up. Yes, it is. Okay. And let's get our closed captions on here. And now we're going to learn about things called, take a look at that word. Say that word aloud to your neighbor. Say that word out loud to your neighbor. Isotopes. Isotopes. Anyone heard of them before? Maybe. There's a few of you. Okay. Let's find out what they are.
What are isotopes? Isotope is a word that gets thrown around in chemistry a lot. So, like, what are they? Really quickly, isotopes are different versions of an element, or different versions of a certain kind of atom. This can be a tricky concept, though, and a lot of people get confused by isotopes. So I want to describe them by starting out with an analogy to cars, okay? I want to talk to you about the made-up car called the Lamona, the epitome of luxury, and it's known for its very distinctive styling. As you'll see, the Lamona looks like a lemon.
And just so you know, a car that doesn't work very well is called a lemon. If you buy a car that doesn't work very well, you say, oh my gosh, I got a lemon.
Now the Lamona...
Because it's sour, I guess. You know, it's like, I didn't want that. I wanted an orange, and here I am, I'm eating a lemon, right? I think that's where it came from. Yes?
Comes in 3 different models. There's the Lamona G, the Lamona GX, and the Lamona GXL. They're all different colors, as you can see, but each of these models also has unique features. One has a radio and leather seats. The GX here has chrome wheels and a CD player. It's blue.
You can tell this is an old video. This car has a CD player. Woo.
The red GXL has massaging seats, platinum spinner wheels, and everything. But here's the point. They are all Lamonas. They're all Lamonas because they all have this distinctive styling. They look like a lemon, and that's what makes a car a Lamona, okay? So it doesn't matter what color it is, and it doesn't matter the various options that you get in these models, the GX or the GXL. What matters is that they all have this particular shape. That's what makes a lamona a lamona. So we have these three different models. I want to use this analogy now to talk about the same thing but with atoms. I want to now introduce you to three models of carbon, just the way there are three models of the lamona. Okay? Here are the drawings of each one of them, and what we're particularly concerned about is the nucleus. I'm using these red dots to symbolize protons, and I'm using the blue dots to symbolize neutrons. The swirly circles are supposed to represent electrons that are buzzing around the nucleus, but we don't really want to worry about that too much right now. Anyway, these three models of carbon are carbon-12, carbon-13, and carbon-14. Let's look at the options in them. Like we did with the lamona, let's look at how each one of these different types of carbon differs. Okay? So if we count the number of protons in carbon-12, we'll see that it has 6 protons, and if I count all the blue spots here, I have 6 neutrons. Okay? Carbon-13, 1, 2, 3, 4, 5, 6 red spots, 6 protons. In this one, I have 7 neutrons, and in carbon-14 down here, I have 6 protons, and I have 8 neutrons.
Okay, now before we let Tyler go on with his thing, what do all of the carbons have in common? 6 protons. In fact, that is what defines an element, an atom, as being a carbon atom. All carbon atoms have 6 protons. Could you please go find carbon on your periodic table? What do you see on carbon that relates to what we just saw with those different isotopes? It is the number 6. And what do we call that number 6? That number 6 is called the, and if you forget, oh, didn't want to do that. That moved everything. Hang on a second. If you want to know what it's called, it actually says on here, the number at the top is called the atomic number. Okay? What does the atomic number tell you? It tells you the number of protons. So if you want to add that onto your periodic table, the atomic number tells you the number of protons, and it tells you the number of electrons in a neutral atom. It means that we're going to get into particles called ions where we either add or remove electrons. Number of electrons in a neutral atom. For now, because we don't know anything about ions, we're going to say yes. It's equal to the number of protons and it's equal to the number of electrons. Okay? It's equal to the number of protons, it's equal to the number of electrons, and we'll worry about the electrons becoming different later on. So for now, atomic number gives you the protons and it gives you the electrons. The other thing I want you to take a look at here, you'll notice that each of these carbons, it's not just called carbon. Remember, like the Lamona wasn't just Lamona, it was a Lamona GX and a Lamona GXL, right? This isn't just carbon. This carbon here is carbon 12. This carbon here is carbon 13. This carbon here is carbon 14. It is the protons plus the neutrons, yes. And what is the mass? What is the mass of one proton? Yes. The mass of one proton is 1. 1 AMU. What's the mass of one neutron? Sit. Turn. Thank you. One proton has a mass of 1. One neutron has a mass of 1. So if you have 6 protons and 6 neutrons, what is the mass? Hold on. If you have 6 protons, what's the mass of 6 protons? 6. So if you have 6 protons and you have 6 neutrons, how many is that all together? 12. So what does that 12 tell you? It tells you the protons and the neutrons, but it also tells you the mass of the atom.
So what do we have in common here? All the different models of the lemona, even though there are things that they differed about, all have the same distinctive lemon-like shape. So for carbon, what they all have in common is they have 6 protons. 6 protons in the nucleus. And that's what makes a carbon atom, okay? So it turns out that it doesn't matter how many neutrons it has. 6 neutrons, 7 neutrons, 8 neutrons, no big deal. It's just like painting the lemon in different colors or adding a radio or a CD player. The neutrons, it doesn't matter. It doesn't change the fact that each one of these are a carbon atom. That's because carbon is defined by the fact that it has 6 protons in its nucleus. If you look it up on the periodic table, you'll see something that looks like this, and the number up here is the atomic number, 6, which means that if an atom has 6 protons, it's carbon. Okay? So that's what these all are. They are all isotopes of carbon. They're different versions of carbon or different models of carbon with the same number of protons and different number of neutrons. So look at how I wrote this. I've got carbon 12, carbon 13, carbon 14 up here. I want to take a minute and talk about the numbers. So the number of protons in the nucleus, we call that the atomic number. You may already know that. And then carbon 12, this 12 that I've written here, refers to a different number, and we call that the mass number. The mass number, as you'll see, is the number of protons plus the number of neutrons. So this is carbon 12. 6 plus 7 protons and neutrons is 13 here. 6 plus 8 is carbon 14 here. So that's how we distinguish between these different isotopes, different types of carbon. There's another way that we sometimes indicate these different isotopes of an atom instead of doing 12 and 13 and 14, and that's by using something called isotope notation. Let me show you how we do that. The way we write carbon 12 or 13 or 14 in isotope notation is we start out with a chemical symbol. If you don't already know that, you can find it on the periodic table. So here it is. It's a big uppercase C. So I start with my C for carbon. And then on the lower corner here, I write the atomic number. So that's going to be 6. And then up top, I write the mass number, which is 12. So this is carbon 12 written in isotope notation. Carbon 13 is going to be 6 again, because all carbon has 6 protons in its nucleus. But then the 13 up here. And finally, carbon 14, written in isotope notation, is C614. So that's how we can write all these isotopes of carbon in isotope notation. Then, of course, you can also write it as just the element name with a dash and then the number. So carbon isn't the only type of element that has multiple isotopes. In fact, just like cars, almost every form of element comes in multiple isotopes. Here are the calcium isotopes, for example. If you look up on the periodic table, you'll see that calcium has an atomic number of 20, which means that any atom that has 20 protons in its nucleus is calcium. But just like with carbon, you can vary the number of neutrons that are in the nucleus. You get all these different isotopes, but you still have calcium. Calcium, we've got 40, 42, 43, 44, 46, 48. All of them have 20 protons in the nucleus, but they have varying numbers of neutrons. Just like we did with carbon, we can write all of these calcium isotopes in isotope notation, where we have the mass number here up at the top, and the atomic number down at the bottom. You'll see they all have the same atomic number of 20, but different mass numbers the sum of protons and neutrons. The same is true for iron, just to give you another example. Iron.
Do you want me to go back? Better? Oh, a little further? His hands are in the way. Yeah. Oh, there we go. It's always hard to get a still of a Tyler video because his hands are always in the way. Yep. Now, getting all of those individual numbers down is not as important as realizing that what is always the same for calcium? Protons are always the same for calcium. The other thing that I want you to take away from this is that if you write the name of calcium, CalCium, the way you tell one isotope from another isotope is by putting a dash. Okay, so you got a dash. And then, what's that number that you write at the end? That's the mass number. What is the mass number equal to? Protons plus neutrons. So essentially, this is the nucleus. Yeah? That's everything that's in the nucleus. Is that number there? Other thing to look at is if you're not writing the whole word, if you're just writing the symbol, the Ca, you don't put the dash and the 40. Where does the 40 go? 40 goes at the top left. Your other right? Your other left? What? Okay. The 40 goes at the top left. And the 20 goes at the bottom left. Okay? Yeah? Left. Oh, okay, sorry. The 40 in the word goes on the right. The 40 in the symbol goes on the left. Yeah. Yeah. Okay? And this tends to be kind of confusing because the periodic table puts the atomic number at the top, and this puts the atomic number at the bottom. So it's a little confusing. But we're going to do a lot of these so that you'll get used to it. And I don't even think we're going to bother with the iron because it's just a lot more numbers. So let's just go through this and make sure we caught everything we needed to catch. There we go. Isotopes are different what? Versions. They have the same number of, yeah. Yes. Borrow the pencil. Okay, so they have the same number of protons, but different numbers of neutrons. the different number of neutrons makes the mass of different isotopes different. Because the neutrons are different, the mass is also different. What does the atomic number tell us? The number of protons and the number of electrons. What do we call the protons plus the neutrons? That's our mass number. Carbon dash 13. What is that 13? That 13 is the mass number. That is the protons plus the neutrons. If we want to write the isotope notation, that's when we use the symbol. Where does the mass number go when we write the symbol? On the top left. So the 13 goes on the top left. Okay, so the mass number in the name goes at the end, but here it goes at the top left. And what goes down at the bottom left? That is the number of protons. I'm going to leave that out for now because like I said, number of electrons will change later on. It's the number of protons, which is called the atomic number. Okay? And you know what the nice thing is? If I said to you, how many neutrons are in an atom of carbon 13, you could say the number of neutrons is 13 minus 6. which is 7. So if you have isotope notation, you just take the top number and you subtract the bottom number. Top number minus the bottom number. So if you have an isotope notation, you can actually figure out the number of neutrons, which is kind of cool. Okay, so here, carbon 12, what's that 12 again? That 12 represents the mass number. Why is it moving rather than doing things? Here we go. And the mass number goes at the top right or top left? Left. Left. Right. Okay, left is that way, right is that way. So on the top left, that's where the mass number goes. Protons, what do we call the number of protons? The atomic number. And that goes at the bottom left. And then if we take the 12 and we subtract the 6, what do we get? 6. So there are 6 neutrons. Okay, and I think we've actually done enough that we're not going to fill in the rest of this right now. What we are going to do is you're going to do the exercises on page 85. And page probably 79, I believe you. 79 and 85. Yep. That's your homework. Yes. Yes, absolutely. Let me find that for you. Did I?
Okay, my academic comeback starts now.
It's here now. I still, every time I look, I'm like I feel like I know, and I do, because I'm like, you're feeling that. But then every time I like doubt myself.
Yeah, and that's okay. This guy is still like,
Okay, yeah.
So I'm okay. Yeah, I'm a hockey tournament. So I won't get to make it. But
Okay.
can I do the quiz once, like, as soon as we get back?
Absolutely.
All right.
Perfect.
It's just on the page.
Yeah, phase changes, diagrams, yeah.
Okay. And I'll get the homework.
Yep. Perfect. Oh, it's flex time. Yay. Okay.